Hello and welcome to another episode of How to Understand X. Today we're going to be talking about series. As we talked about in the previous video, sequences are just assemblies of objects that, for our purposes only use integers as valid inputs to get valid outputs. And a series is just the sum of every term in the sequence. But there is a lot to series and a lot to talk about today. So, with our definition of a series, like I touched on in the previous video, a series is just the sum of terms in a sequence. For our purposes, these are going to be infinite sequences, and I'm going to focus on infinite series, and I'm going to be using it interchangeably with the term series itself, but the sum of terms in a sequence not in a sequences. The sum of terms in a sequence isn't necessarily the infinite series, right? We use sigma notation, saying that if you start from n equals 1, or the first term in some sequence a sub n, and you go to infinity, this is the infinite series for a sub n, right? You start at a1 plus a2 plus a3, and you just go on and on until you get to a sub infinity, even though that's not real. So we just use the ellipses to denote that it's going to go on forever. But we can also do partial sums. This can also sometimes be like, I'm not really sure if they call these series as well, but this is a partial sum in which you are adding up to this is going to be the last term in this partial sum. And we will do some partial sums. I was going to do like an addendum video to my sequences video talking about stuff like arithmetic sequences and geometric sequences, in which case partial sums usually have some interesting properties about them. But for us, we're going to be talking about infinite series, and we're going to be talking about mainly convergence and divergence of these series, because they do converge to values or they do diverge to infinity, but we can't really calculate what they do, right? We can approximate, we can think, say, in terms of limits, like with functions. You don't know exactly what f of infinity is, because infinity is not a number, right? And if you just go out to infinity, you can say it's tending towards a specific value. There is a limit that exists, and you are going closer and closer to that limit, but you don't actually know what the value equals, because you can't calculate it. You can't go all the way to infinity and do that. And there's a similar concept within series. We're going to talk about converging series, but the same idea applies, that you can't really add up all of these terms within our lifetime, because there is an infinite number of terms, a countably infinite number of terms, of course, because we are usually using a sub n within n in natural numbers. There is a therefore countably infinite number of inputs, and therefore a countably infinite number of terms. You can technically add up and get a value. Well, it's going to be infinity if it diverges, but the idea is generally the same. You can't really calculate it because you can't add an infinite number of things, but you can say that this tends towards a specific value, or you can at least say that the series itself converges to something. That's why for series, for the most part, you're not going to be actually calculating what the sum is. You're just going to say whether or not it converges to a value or not. And so we are going to say that a series, like starting at n equals 1, going to infinity, of a sub n, converges when there is a real limit. If there is a limit that exists for a sub n, then the series converges, and if there is not a limit, then the series diverges. And we can also talk about, uh, well, okay, wait, let's think about it. So, as I said about partial sums, you can think of a series as a sequence of partial sums. That sounds a little bit confusing, but I think let's write it out. So you have n is equal to 1 a sub n, right? And we can write this as the limit as n approaches infinity of a sequence of partial sums. So the idea behind it is that if every single term is a sum of previous terms that came before it, then the new sequence that is created is just a sequence of previous partial sums. Like, if you evaluate the sequence as just the addition of new terms for every previous term, you are going to get a series, right? Because every new value is going to be added to what you had originally. So if S sub k is a sequence of partial sums, or, the sequence of previous outputs that you're adding, well, the sequence of outputs that you're adding to your previous outputs, then if you think of a series as just the addition of every single term, you can think of series is as just the sequences of partial sums. And a series, if it is equal to the sequence of partial sums, if this limit exists, then this series exists. And you can also write this as the limit as k approaches infinity of, starting at n equals 0 to k of a sub n, right? So when the limit of the partial sums exists, right? Like when the value of the series exists, we say that the limit as k approaches infinity, when you go from n equals 0 to k of a sub n, is going to be the sequence of partial sums. And so if you have, what's a good way of describing this? Like if you think of, let's talk about one of the most common converging series that you're going to see, and that is a geometric series. So I won't, I'll define geometric series, of course, in a second, but this is the geometric series. Well, one of the most common geometric series, 1 over 2 to the n, right? If we say that a sub n is equal to 1 over 2 to the n, we say that if n is equal to 0, we'll start at 1, right? And then you'll go do 1/2, 1/4, 1/8, and, on and on. And we can say that the series looks like this. It looks like 1 plus 1/2 plus 1/4 plus 1/8, and then on and on. As you can see, this every subsequent term is smaller than the one that came before it. And if you think about this, just within the context of a series, if this is, the beginning sequence, this will be a partial sum of the previous terms that came before. Since we're starting at n equals 0, there were no previous terms. And then you add this next term, right? K is equal to 1, and then this becomes a new partial sum. K equals 2. This becomes a new partial sum. K equals 3. This becomes a new partial sum, and the limit as k approaches infinity of S sub k, or the sequence of partial sums, should be the same as this series itself, the value it goes to, if and only if this series converges at all, which we will, try and prove. So yeah, I think that's perhaps a slightly confusing idea, but just like to sort of reiterate what we've been talking about. A series converges if um, when you add every single value, you are getting very close to one real limit. And you might be thinking, if a series is a sum of infinite terms, shouldn't I get an infinite value? And that's partially why it's so difficult to actually calculate the sums themselves, but it is important to recognize that even for this series, which I'll just, spoiler alert, tell you that this series does converge to one value. As you can see, I'll go out just a little bit more. Plus 1 over 16, plus 1 over 32, plus 1 over 64. Once you get to higher and higher values of n, right? If this is n equals 0, and 1, and 2, 3, 4, 5, 6, as you get to higher and higher values of n, each term is getting significantly smaller, exponentially smaller. And the values, once you get to, say, n is equal to 20 or 30, and, because we are going to infinity, you should be going to like 100,000, you should be getting to really, really high values. And if you do 2 to the 100,000 to the million, you're getting to such small values that the amount of units that you're adding are basically negligible. That's the idea behind a converging series, that once you get to a certain value of n, you aren't really adding anything substantial, and you are getting to one real limit value, right? So let's talk about the types of series. I'm going to very briefly go over what each of them is, and then we're going to talk more about the convergence and the intricacies of them, but it's important to just sort of see what they are before we get really into it. So I talked about it earlier. A geometric series is one where each term is multiplied by a ratio, or the common ratio. So let's go back to 1 over 2 to the n. This is the same as 1 over 2 within parentheses to the n, right? Because 1 to the n is always going to be 1 for every integer value of n. So if we start at n is equal to 0, we have 1, 1 half, 1 fourth, 1 eighth, 1 16th. And I know I'm going to have to erase this and rewrite it, but I'm going to try and keep this strictly series notation from now on, because, we will, sequences are obviously important to series because that's what series are, but I'm going to talk about geometric series instead of sequences, because partial sums of geometric series are their own sort of thing. So plus 1 over 16 plus dot dot dot, and then we say that the general term is 1 over 2 to the n. The general term is just what each input is being plugged into. You can think of it as the sequence, but it usually doesn't involve the first value. Well, I won't say usually, because there's always going to be some edge case where something really crazy happens. But if you have a function that is altered, we will get to Taylor series and approximations in a little bit, so I won't be as coy then. But when you're writing the general term, it's just what the you know series is even representing, what each n value is being plugged into and what the output is. And this is a geometric series because you have an a. We say that the a is the first term, right? And then we have an r, or a common, we have an r, or a common ratio. And a common ratio is just exactly what it sounds like. It's a ratio that's being multiplied to every subsequent term within this series. So times 1 half, times 1 half, times 1 half. I should use, multiplication like that. so it's easier to see, but you're multiplying, 1 times 1/2 times 1/2, 1/4 times 1/2, and on and on. So the ratio that is being multiplied between every single value is common, and that r is 1/2, at least for this geometric series. And a general way of thinking of it is if you have this value to the n, then we can say that this is r to the n, right? R to the n. And we will be talking about how these converge. Oop, got a little bit ahead of myself. We have some r to the n, right? R. And we will talk about how this would converge and like what values of r satisfy the important like conditions for a geometric series to converge. But yeah, this is one of the few series that you can actually get values for if it does indeed converge, and we will talk about how that works and why that works in just a second. And now we're going to talk about the harmonic series. This is an important diverging series. It is 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. I'll write this out. Harmonic. 1 plus 1 over 2 plus, not negative 1, I'll just put equals, plus 1 over 5. And then, as you may be able to notice, you can think of this as 1 over 1. The general term is 1 over n, right? As you are increasing the n value, the denominator is incrementing by 1, and this series is divergent. We'll try and prove this in a second, but just take me for my word on this one. This one does diverge, and the fact that it does diverge is actually really helpful for proving other series that diverge or converge. And I haven't even talked about conditional convergence. We'll talk about that once we get through all of these series. And again, you're gonna take me on my word for this one. If this is the harmonic, we can say that there are alternating series. A very useful alternating series. So an alternating series is just something that is being multiplied by an alternating plus or minus, right? And negative 1 to the n is a very good alternating thing. If you just sort of think of it, if you have only integer values of n, you can only have odd or even values of n, and for every odd value you will get a negative number, and for every even value you will get a positive number. And then, for example, if we say that, well, let's do negative 1 to the n plus 1, so that we can start with a positive n equals 1. Like if we think negative 1 to the n plus 1 and n is equal to 1, we're going to have a nice and positive negative 1 squared, which is positive 1, of course. And so let's try and make this harmonic series into an alternating series. We can start with 1 still, right? We're working with, let's write our general term. We're going to say this is negative 1 to the n plus 1, right? Because we want our first term to be positive, times 1 over n, or just put this in the denominator n. We're going to have 1 minus 1/2, right? Let's plug in n is equal to 2. You're going to have negative 1 to the third power, which is negative 1, over n is equal to 2. So negative 1/2 plus 1/3 minus 1/4 plus 1/5, and then on and on. Right, now you're going to put your general term, and this actually does converge. But we'll talk about why this converges. There is a test that proves why certain alternating series are able to converge and why others are not able to. But an important idea to grasp about this, just like, you don't really need to understand it too well because we will go over it in further depth in just a second, but just something to remember. If this is divergent, right, the value is going to infinity, the series is going to infinity, and this is convergent. As you can see, this has negative values, right? And though you do have a strictly monotonically decreasing sequence, the series only converges if there is an alternating part when you subtract every other term, which will get you a significantly smaller value than a harmonic series, the one that does not have every other term taken out of it. But it is still important to remember that a series is considered uh, conditionally convergent. Conditionally convergent if, well, I should probably define absolutely convergent and then use conditionally convergent as the opposite of that. But absolutely convergent is by definition not going to be any alternating series. Absolutely convergent series only apply to series in which every single term, if you took the absolute value of every single term, like for example, if the harmonic series was not divergent, if the harmonic series was magically convergent, and you took the absolute value of every single term and you add them up together, and you still got a single real value, that would be absolutely convergent. And any sequence or series that is not absolutely convergent is either conditionally convergent, in which it converges but the absolute value of every term does not converge, well, the sum of every absolute value of every term does not converge, or it just diverges. So you can only have conditionally convergent, um, absolutely convergent, or divergent. And of course, you can have oscillate. You know, you can have -1, 1, -1, 1, and just on and on, because you're not really diverging to infinity. You're just oscillating between the same values. But we can still think of it as diverging. So we got through two types of series so far, and we can also talk about another relatively fun one, in my opinion. We have the telescoping series. So if we say that if you start at n is equal to 1 and you go to infinity and you subtract b sub n plus 1 from b sub n, right? If you subtract every other term or every subsequent term from the term that came before it, then, well, let's just try and draw this out. So we have b1 minus b2 plus b2 minus b3 plus b3 minus b4 plus b4. That's how it'll look, right? Like if you plug in 1 and then 1 plus 1, you'll get 1 and 2. You plug in 2 and 2 plus 1, you'll get 3. Well, 2 and 3. And as you can probably tell, the only thing that has not been canceled out so far is the first term. And this is the second type of series that we will actually be able to solve. And it's probably the easiest one to conceptually sort of see if you are subtracting a subsequence or a smaller sequence that exists within a larger sequence. If you're subtracting a subsequence that is only one term off from the original sequence, then the only term that is left, or the limit, or the value that the series converges to, is going to be the first term, right? Because every other term is being canceled out. That's how the subsequence was originally defined. It's b sub n plus 1, right? So the only value that you're left with is the first value. So that's just what this is equal to. So I'm just gonna write that out, b1. But we can describe that as a test in a little bit. And we're almost done with just kind of blitzing through these. I promise we will go through these in more detail in a second. And we have 1 over n to the p, right? This is the last one that I'm just sort of going to define. We're going to say you start at n is equal to 1, you go to infinity. This is a p series, where p is the degree of n. And for example, if p is equal to 2, it looks like 1 over 1 squared. We can write that out. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and on and on. This might look like a geometric series, but just remember the n is incrementing. So it is not the degree of every term, it is the, it is the degree, not the degree, it is the actual like value that is being raised to a specific power. That is what is increasing. And this is a p series. This is also convergent for specific values of p. And if you took what I said at face value about a harmonic series, you might already have a guess for what values of p actually converge and what values of p diverge. Like we said, if p equals 1, then you have n to the 1, which is n, right? N to the 1 will equal just n. So you're going to have 1 over n, and you will have a divergent series. You're going to have just the harmonic series again. And as we said, this series does indeed diverge. So p, if p is supposed to, if a p series is supposed to converge, and we said that 1 over n diverges, we're going to need values of p that are greater than 1, because if p is equal to 1, we just go to the harmonic series, which we said diverges. And yeah, I think that's probably a pretty solid definition. I wouldn't say solid. I'll just say it's a very brief introduction into what these series really are. And now we're going to talk more about how they work and some of their deeper ideas. So, now that we have some of our definitions down, at least a little bit, let's talk about what we can do to prove whether certain series converge or diverge. As we touched on this beforehand, a series converges if it has a limit that it approaches, and it is divergent if it does not. And the first and most important test for any series that you are trying to evaluate or determine the convergence of is the aptly named test for divergence, also known as the nth term test. You might also hear this being called the limit of the summoned, or like, a bunch of random names, but it's a very simple idea. And once you see it, you're gonna say this is pretty dumb. Like, this is relatively obvious. But if the limit as n approaches infinity of a sub n does not equal 0, then the series of n is equal to 0 to infinity. We're going to use 0 and 1 interchangeably because it honestly depends on your definition of the natural numbers, whether 0 is included or not. I tend to go with the idea that 0 isn't included within natural numbers, like you start at 1 and you go to infinity, and 0 is just an integer. But honestly, like for just proving convergence, n equals 0 and n equals 1 aren't super important. I feel like I'm going to regret that very quickly. But the limit of n approaching infinity, no, the limit as n approaches infinity of a sub n, if that does not equal 0, then the series from n equals 0 to infinity of a sub n diverges. And that was a lot of words to explain something that I would say is relatively obvious. We touched upon this before, but for a series like, say, 1 plus 1 half plus 1 fourth plus 1 eighth plus 1 16th, if we assume, just like automatically, if we say that for some reason this series does converge, every single value has to be less than the one that came before it. Or it doesn't necessarily have to be less, but every single value needs to be getting closer and closer to 0 as you increase n, right? Because if you have like 1 over 2 to the 100,000, you are getting to very, very small values, and you're essentially adding 0, right? You are getting a sum that is only being very slightly changed by minuscule values. And if you have a limit that is not 0, for example, just for, you know, just for saying it, let's say that the limit is equal to 1, right? Let's say that the limit as n approaches infinity of a sub n is equal to 1. Did not give myself enough space. Let's do that one more time. We have the limit as n approaches infinity of a sub n is equal to 1. Let's assume this is true, right? If we start at n is equal to 0, and since the limit as n approaches infinity of a sub n is equal to 1, I'm just going to sort of say that every single term, you most likely will not have the first couple of terms equal 1 exactly, but let's just say that some values are happening up in the front, some stuff is going on, but once you get to higher and higher values of n, you're just getting closer and closer to 1, right? And say this is n is equal to 100,000, right? Some really big value of n, then you have 100,001, 100,002, and yeah, that's too many zeros. 100,002, and on and on. But you are adding 1, right? And if you just sort of look at it, if you keep adding ones, you are not going to be going to a single real value. You are getting closer and closer to infinity, right? Because your series is constantly increasing. It's not, well, I mean, series are always increasing, but you aren't getting closer and closer to one value because every single term is adding an extra 1 at the end of it. So, like, I feel like I'm not explaining this very, you know, efficiently, but the idea behind it, I would say, is relatively simple. Like, if you get to very high values of n and you aren't basically adding 0, then the sum of an infinite number of terms isn't going to be a single value. It's going to be infinity because you're going to keep adding 1 for every possible value of n, right? And that's the nth term test. I would say it's relatively normal, if you just think, hey, if I'm trying to get to a single series value and I take the limit as n approaches infinity of the sequence that this series is made out of, and it does not look like it's approaching 0, then I will not be adding 0. Once I get to higher values of n, I'm still going to be adding things to my series, and my series will not converge to a specific value, which means that the series as a whole diverges. And yeah, I mean, you know, relatively solid as an idea, but because it's so, dare I say, simple, um, it is usually not the end all be all. If the limit does equal 0, if the limit does equal 0, then this test is inconclusive. For example, as we said, 1 over n is a series that is divergent, but the limit as n approaches infinity of 1 over n is equal to 0, which means that the test can't always be true, right? So we have to say that if the limit does equal 0, it is inconclusive, and we have far more work to actually write. So now that we have our test for divergence and we say that this test is inconclusive if the limit is equal to 0, let's talk about a more definitive test, but a somewhat more annoying test, at least to actually calculate, because it does require some improper integral thinking. But I think I don't know. I think it's pretty important, and the idea behind it is really nice. So the integral test, um, again, there are easier tests than the integral test, and we will get through some of them in just a second. But this is like the basis for quite a few future tests, or at least one or two future tests. We're gonna have the idea that if f is continuous, positive, and decreasing, because again, we can only calculate series if the sequence is monotonically decreasing, if there is a value that you are converging to that is 0. And let's say that this is on some interval k to infinity, right? And f of n, like a function, is equal to a sub n in terms of the actual values that are being plugged in, then we say that the integral from k to infinity of f of x dx is going to be compared to the series from n is equal to k to infinity of a sub n. Now, if this is divergent, then this is divergent. And, well, technically the first part is if it's convergent, then this is convergent, but sort of mix up the order. It doesn't matter. If the integral is convergent, then the series is convergent. And if the integral is divergent, then the series is divergent. Relatively easy to remember, but let's actually try and prove how this works. It's going to be a little bit less math speak and more like just looking at this. But again, let's rethink. We have f is continuous, positive, and decreasing. Continuous, positive, decreasing. Let's remember that. And let's draw a continuous, positive, and decreasing function. So let's say that we have a function that looks like this, right? And for the sake of argument, let's say that this converges to a specific value. The area under the curve, or the integral from infinity to k, which we will say that k is equal to 1. You can do n is equal to k. Well, I'm saying that wrong. So let's say that, you know how we, in our formal definition, said that we are going to use k is equal to, well, we're going from k to infinity. We're going to start with n is equal to 1, because that's easier to, like, illustrate, and, you know, it's easier for me. So if we have a function, this is f of n, right? And we have this series, or sequence, a sub n, which are the dots. Let's draw 1, 2, 3, 4, 5, 6, and we'll just put these little dots to show the values that we're at right now. I know it's kind of hard to be accurate with this, but we can say that if we have, well, let's try and prove the slightly more difficult one first. Let's say that if we have a convergent f of n, we want to have a convergent series of a sub n, right? So if the series converges, that means that the width, so if this is n is equal to 1, then the value that's being added is this y value, right? It is the height of this little rectangle. This is sort of like Riemann sums. And the width is going to be 1, right? Because it can't be, how a normal integral works with just very thin rectangles, right? If you have this, and the width of the rectangle is dx, an infinitesimally small value, we can't have that happen because we need to have integer term values, right? So we're going to say that n is equal to 1, n is equal to 2, and I hope you can see that f of 1 should equal a1, and f of 2 should equal a2, and on and on. Each of these values are the heights or the outputs if you plugged it into f of n, and each term, well, each like nth term is going to be the nth input within f of n, and the area of this like assembly of rectangles, we're going to have this height, which we said was f of 1, or, well, since we're starting at n is equal to 1, I think, let's see how we're doing this. So if we're starting at 1, we're not including that last rectangle. So we actually don't include f of 1, I don't think. Yeah, I think, well, let's see. So, I'm going to say that the area of this thing, we're going to say that this area starts at 2, because I know that we have to include an n plus 1 area, just to show that n, if the nth like sub series converges, then the n plus 1th, or if n plus 1 converges, then n converges because n is less than n plus 1. But yeah, let's just say that a, or the area of this assembly of rectangles, is equal to 1, which is the width that we've defined, because this is continuous unnatural numbers. We're going to say f of 2 times 1 plus 1 times f of 3, and on and on. But this is also equal to a2 plus a3 plus a4, which is again a series, right? We're adding from I is equal to 2 to some value of n, and this is well, a sub I, because we're using I as our inputs instead of n's. So if we have I equals equal to 2, we're going to n a sub I. This should be a sub 2, right? We're adding these values, and we're getting closer and closer to a sub n. The reason we're starting with I instead of n is because we don't actually know what n is, right? N is supposed to be infinity, because we're doing the limit as n approaches infinity to get this thing that should converge, but we have a sub 2 plus a sub 3 plus on and on until you get to a sub n. And we are saying that since all of these rectangles are less than their actual y values on f of n, that this is supposed to be an underestimate, right? So we're saying that this series from I is equal to 2 to n of a sub I should be less than the integral from 1 to n of f of x dx. So from this, the second term upwards, the series, if it is an underestimate, should be less than the area under the curve of 1 to infinity. So if 1 to infinity of f of x dx converges, so let's write that over here. If 1 to infinity of f of x dx converges, and this has a finite value because it does converge. That means that if we don't know what n is, we say 1 to n. If n is just a real number that we can like say like definitively that n is this value, because n can truly be anything, but let's say n is just a number, right? Let's how am I gonna describe this? I saw this proof like a long time ago, but I need to re-look at it. So this the area under the curve for this interval is going from 1 to n. We're defining n as some random number that we are getting closer to, just so that we can say, well, improper integrals are a lot more finicky to work with, but we'll say that this is n, right? You are getting rectangles that are approaching to n, and if we have this partial sum from I equals 2 to n, that will be less than the integral from 1 to n of f of x dx, and infinity is greater than n, so n from 1 to n of f of x dx, that integral should be less than this integral. So we can write this as an inequality, right? Let's just rewrite what we've sort of got down. We have the series from I is equal to 2 to n, or the partial sum, a sub I is less than the integral from 1 to n of f of x dx, and that is less than the integral from 1 to infinity of f of x dx. Right? And since our series starts at I, the reason that we started at 2 is, again, we know that 2 will be an underestimate regardless of what n equals 1, that f of n value is. Just like within the context of this like graph, if you just look at it, if we're doing 1 to infinity, all of this area under the curve, and we're doing this, these rectangles starting from that x value, you are going to have an underestimate regardless, right? And we're just trying to prove that this underestimate starting at I equals 2 is still valid for I equals 1. So yeah, I'm sort of learning this proof now. I got it up with me and I'm trying to reason through it in my head. But I think it makes sense, sort of. Like, the idea is if you start at I is equal to 2, you are definitely going to have an underestimate. Regardless of the I equals 1 value, which we as of now do not know, we have to agree that if I equals 2, we will have an underestimate because the all of the rectangles will be one shifted up from the normal integral. And the integral is already area under the curve, which we are assuming to be larger because these rectangles should be an underestimate as we have drawn. But if we have the series from I equals 2 to n, the series from I equals 1 to n of a sub I is equal to a1 plus the I equals 2 to n of ai, right? And again, this is the same sort of idea behind what we originally were talking about with what a convergent series even is. It includes the limit of some sequence of partial sums, which is what every series truly is, right? It is every subsequent term is just the addition of previous outputs to a new sequence that you are creating with every previous output. So if this is the thing, if this is the series from I equals 1 to n, then we can also say that this has to be less than a1 plus the integral from 1 to infinity of f of x dx. right? Like if we added a1 to both the bottom or the lower bound and the upper bound, then, well, if we have to add to the lower bound, we'd have to add to the upper bound, and we are saying that um, this series is less than this plus a1, right? And that means that this sequence, the sequence of partial sums, or like we said, the very beginning of this video, limit as k approaches infinity of s sub k, if this is the sequence of partial sums, this is equal to that, right? This is the limit itself, and this is bounded above by this value, right? Every single value that this could potentially be is less than the maximum value that this can be. So since we assumed at the beginning of this that this is convergent, and we added this value, and this is still less than this value, that means that this series is convergent because we said so. I'm hoping this makes sense. If it doesn't, I will obviously, do another video and we will get through it in perhaps a slightly more researched and well-informed manner. But I think that makes a good deal of sense. And it just sort of looks right, if we say that this is an underestimate and you are drawing little rectangles underneath it. And, well, the rectangles have to be accurate, right? Because the height is still f of n. As we said, f of n is equal to a sub n. So every n value, so every height of these rectangles is equal to the actual term that it corresponds to. So f of 1 is equal to a1, f of 2 is equal to a2, and on and on. So the series and the sequence, the sequence and the function both have the same outputs, but the actual area is different because sequences are, again, only continuous for natural numbers and for integer values, so you're only going to have widths of 1. You're not going to have infinitesimally small widths, so you're going to have rectangles that have widths of 1, so you're only going to be adding up these heights. Okay, now let's get to the slightly easier idea to sort of look at and to understand. We have, from 1 to infinity, the same decreasing positive continuous function f, and we're going to start at 1, and then we're going to go to n. If we start at 1 and then just go over, right, we start at the actual value and then go over 1, so 2, 3, 4, 5, 6, and on and on. As you can see, this is an overestimate, and the area is going to be, well, up to here is where it'll stop, right? That'll be n minus 1, that term. So the area is going to be f of 1, or the height of that rectangle, f of 1 times 1, or the width, right there, f of 1 times 1 plus f of 2 times 2 plus f of, not f of 2 times 2, sorry, f of 2 times 1 still. The width is always 1 because this is, again, natural numbers. Everything is incremented by 1. So f of 2 times 1, f of 3 times 1, and then on and on. And then from here we have like little ellipses just to show that this goes on forever. Well, not forever, until you get to f of n minus 1 times 1. Again, n is not included because this is an overestimate. We're starting from the left. So f of 1, again, is equal to a1. F of 2 is equal to a2. And on and on. So this is the partial sum from I is equal to 1 to n minus 1 of ai. And again, this is sort of like Riemann sums. I probably should have explained the like convergent idea a little bit more, but if you thought of that as right Riemann sums and this is left Riemann sums, for decreasing functions, left Riemann sums are overestimates and right Riemann sums are underestimates. So we have the partial sum from I equals 1 to n minus 1 of a sub I, and this is a1 plus a2 plus a3, and on until you get to a sub n minus 1, and we are saying that this is greater than the integral from 1 to n minus 1 of f of x dx. Right? And we are saying that if the function is divergent, then the series is divergent, so we're going to say that 1 to infinity of f of x dx, this integral, is divergent, which means that if we have this integral adding 1 to this, we're going to have 1 to n, this has to diverge as well, right? Because if this n is approaching infinity, then since f of x is always positive, we are going to have values that approach infinity. And since n minus 1 approaches infinity, n will approach infinity. If you add 1 to both sides, infinity plus 1 is still infinity. And so if we agree that this is true because this is true, then if you subtract 1 or add 1, n minus 1 approaches infinity, n approaches infinity. So yeah, I mean, pretty cool. I'd say it's pretty helpful. You might not seem it, but just like if you want to sort of like digest that stuff that just happened, just think of it as if the function is convergent, that means that you're going to have an underestimate of the series, right? Because series are just little rectangles with widths of 1 that represent the heights of the rectangles, which are indeed the f of n values for each valid value of n. So if you have these heights times 1, which is just going to be the heights, you are essentially getting the same series, right? And if the function, if the integral you defined is convergent, and you know for sure that this series is less than the actual integral, which you said was convergent, then the series has to be convergent, right? Because, I mean, you said that the series was an underestimate of the actual integral, because it's like a right Riemann sum, you know? It's just like triangles, or what? It's like rectangles that you are connecting to the rightmost value, that is, touching the function itself. And if the function is divergent and the left Riemann sum is an overestimate, if the integral itself is already an overestimate, well, not if the integral itself is already divergent, and this series is an overestimate because it is a left Riemann sum, that means that the series itself is divergent. It's a lot like Riemann sums in terms of how it looks and how it works, but I hope I didn't confuse you too much. Idea is still the same. If you have an integral that converges, you will have a series that converges, and if you have a integral that diverges, you will have a series that diverges. And again, like I said in the sequences video, it is important to realize the differences between sequences and functions. Like, the only reason that we're able to use this integral test is because functions and sequences are inherently different. Functions are continuous for all x, while sequences are only continuous for natural numbers. or integers, but usually natural numbers. So yeah, that's what the integral test is, and we can actually, sort of go through a little example of the integral test and how it works, and we can define, or not define, we can show why this ever elusive harmonic series is divergent. So let's do the integral from 1 to infinity of 1 over n, right? And let's see. All right. 1 second. We have this 1 to infinity, right, of f of x dx. This is the harmonic series where it looks like 1 plus 1/2 plus 1/3 plus 1/4, and on and on. And we are saying that if this if this integral is divergent, that means that the sequence itself is divergent. And I'm actually going to, the series itself is divergent, and I'm actually going to use 1 over x notation just because it's easier to sort of wrap your head around. And again, this is connecting back. This is a function. We are going back to function land, at least for a little bit, to prove why the series itself does not converge. So we do this integral, right? We have, well, let's actually write down what we're doing. We're doing the limit. It doesn't matter what you write. The idea is still the same. You are doing some variable that is approaching infinity, and you just rewrite the bounds so that you don't have an improper bound, right? You can't take infinite area under the curve, so you just rewrite infinity as b or t or whatever, and you do the integral from 1 to b of 1 over x dx, or 1 over x with respect to x, and now you have the limit as b approaches infinity of the integral of 1 over x, as we've said many times, is ln x from 1 to b, right? And so you plug in these values, you have limit b approaches infinity of ln b minus ln1, which is 0, so we'll just cross that out. And now you have the limit as b approaches infinity, which is ln infinity or infinity, right? And again, ln is the slowest moving, slowest increasing infinite function, but it is an infinite series or infinite sequence. The limit as b approaches infinity of ln b is going to be infinity, so this integral diverges, which means that the series, which is already an overestimate of this integral, will also diverge. So yeah, that's why the harmonic series diverges, and we're going to talk about p-series a little bit further. This is a corollary of that integral test, and the p-series test only works because of the integral test. So let's try and draw this out. So let's try and do this p-series test within the context of the integral test. We established what the integral test was, and the p-series, if we remember, is 1 over n to the p of some series as n is equal to 1 going to infinity, or n equals 0, whatever. But the idea is still the same. You have some n, and that is being raised to a specific power of p. So now let's format this as a function of x. F of x is equal to 1 over x to the p, right? And we're going from 1 to infinity. So let's do the limit as b approaches infinity of 1 to b x to the negative p dx, right? Because, anything to a negative power is 1 over that power. So we're going to have two possible situations. I see if we have p equals 1, we have our ln b minus ln1, which again we said was 0. So we have ln b if p equals 1, as we said, this is the harmonic series, so of course it's going to equal ln b, which again was infinity, or if p does not equal 1. And that's the more interesting sort of thing. So if p equals 1, you get ln b, which goes to infinity, right? Or if p does not equal 1, well, let's think. We have x to the 1 minus p over, well, let's actually write out what we're thinking. We have x to the negative p plus 1, right? Within our, integration rules, you have x to the n plus 1 over n plus 1, and if n is negative p, you have negative p plus 1. So just for the sake of, easier writing, we can say that this is x to the negative, or sorry, literally just wrote that, x to the 1 minus p over 1 minus p, right? And so we can say it's either ln b or b to the 1 minus p over 1 minus p, right? And yeah, so if you had 1 plugged into here, well, if you had b approaching infinity, you would have something completely different. But if p is equal to 1, you have b to the power of 1, which, if b was a real value, which it's not, if b was a real value and you raised it to 1 minus 1, which is 0, you'd get 1, and 1 minus 1 is still 0 in the denominator. So you'd have 1 over 0, which is, of course, infinity. Well, just in case we needed to review it, it's just if you divide a normal number by a very, very small number, you're going to have a very, very large number, right? So that's why 1 divided by 0 is, it's not equal to infinity, but it tends towards infinity. Oh, and I almost forgot, we also have to subtract a 1 to the 1 minus p over 1 minus p. I'm running a little bit out of space, so I'm going to erase this ln b, just because we talked about it previously, so I feel like it's not really important if we go over it, but, again, if p is equal to 1, we're going to get a harmonic series, which we've established in 2 different ways will get us a divergent sum. So we have b to the 1 minus p over 1 minus p minus 1 to the 1 minus p. I'm going to leave this as just 1 because 1 to the power of anything is 1. 1 over 1 minus p, right? And so I am going to re-plug in that limit as b approaches infinity, but I'm going to factor out some 1 over 1 minus p stuff. We can factor out that 1 over 1 minus p from the b to the 1 minus p, and we're going to have 1 over 1 minus p times the limit as b approaches infinity of b to the 1 minus p minus 1 over 1 minus p, right? And so 1 minus p, we're going to say is greater than 0. If we think about this sort of logically, and sort of just looking at this, let's think of 1 minus p as potential values. So let's say that 1 minus p is, let's say it is less than 0, right? 1 minus p is a negative number. Oh, it's, just ignore what it looks like. Say 1 minus p was like y or something. Just keep it in your head. Just this expression, ignore what it means, just 1 minus p. If this 1 minus p was a negative value, you'd have b to a negative value, right? You'd have 1 over b to some power, and 1 over b to some power would be 1 over infinity, right? Because b is approaching infinity. So if you have 1 over infinity, you're going to have 1 over 0, which is a real valid value. And again, p is going to be an actual value if 1 minus p is less than 0. And if 1 minus p is greater than 0, then we do have a divergent series, like, because if you have b to a positive power, b is still going to be in a numerator, or b b over 1, if that's the fraction that we're thinking of. B will be the numerator, 1 will be the denominator. And b to a positive power will result in infinity if you if you plug in infinity for b. So if 1 minus p is less than 0, right? If 1 minus p is less than 0, we say that this is converging, right? This is 1 over b to some power, because this will be negative. And if we have 1 over b to some power, we will converge to 0, or to some real value. So 1 minus p less than 0 is convergent. And 1 minus p is greater than 0, we will say that this is divergent, right? Because if you raise 1 minus p, well, if you raise b to a 1 minus p that is greater than 0, you are going to have a positive exponent, which would get you infinity when you plug in infinity. So, again, this is just basic sort of inequalities. We'll move this p to the other side, flip this bad boy, and we're going to have p is greater than 1. We would get something that converges, and when p is less than 1, we will get something that diverges. And when we said p is equal to 1, that also diverges by the integral test. So we have when p is greater than 1, this p series converges. And when p is less than or equal to 1, it does not. It diverges. Trying to think if it oscillates or not. I don't think it does. I think it just diverges. Just trying to see if there's like a negative 1, 1 situation, but no, it just diverges. And yeah, pretty solid sort of idea there that we have. And I think it makes sense within the context of our work so far. And again, it's pretty easy to apply. Like, for example, if you have 1 over n squared, you can be like, hey, 2 is greater than 1, that converges. And if you have 1 over n, the square root of n, you'll be like, well, n squared of n is n to the 1/2, and 1/2 is less than 1, so diverges. Like, it's not super thinky, but it is an important concept to remember, and hopefully you understand where it comes from slightly better. And now we do have quite a few more, I should say. We have the geometric. This one I've been foreshadowing for quite a while, but let's actually talk about how geometric series are built and how the sum even works. So this is actually, in contrast to all of our other proofs, a very nice and easy proof if we acknowledge that geometric series converge. Actually, proving that they converge is a different thing, but finding the sum for what they converge to is a lot easier. And so let's talk about how geometric series look. We talked about this earlier. We have a series as n is equal to 1 to infinity, right? And, or n equals 0 or k equals 0, whatever. But you have let's start with 0, just to really show off these series. You have n equals 0 to infinity, and we will have a times r to n, right? As we said, a is the first term. It's what everything is being multiplied by. We have r, which is the common ratio, what you are multiplying. Well, it's not a constant that is being multiplied to every term. It is a ratio that is being multiplied to every previous output to create a different output for the subsequent term. So a is like stretching a sequence. No, that's not a great metaphor. It's more like a is just a common factor, while r is something that actively changes the output, like, and how it converges. I know that's not the greatest, but a doesn't change, r is continuously multiplied because, again, it is being raised to a power. But you have a, which is the first term, and you have r, which is the common ratio. So if we were to expand this, you'd have, well, if n is equal to 0, you'd have a, which is the first one, because anything to the power of 0 is 1, a plus ar, right? Plus ar squared plus ar cubed, and on and on. And we are going to try and find the sum. We're going to sort of agree that this series converges, but we will talk about why it converges in just a second. We're going to say that the sum is s, and we're going to say a plus ar plus ar squared plus ar cubed, and on is what this series looks like, right? And we're going to multiply every term by r. Bear with me. We have a r plus, I'll actually shift it over to the right a little bit so we can have a nice looking thing happening. Wait, you have rs, oh, you have rs is equal to a r plus a r squared plus a r cubed, and then on and on. As you can see, if you multiply r to every subsequent term, you're simply increasing the degree by 1, but a, since it is a common factor, is not changing for any of these. So if you did s minus rs, if you did this sequence, or this series minus this series, this is the first term, and that is one thing that is not subtracted from this rs, and you have the last term, right? If this goes to a to the a times r to the n, you are multiplying a r to the n is the term that comes before a r to the n plus 1, right? Because you are multiplying by an extra r, so you're going to have a minus a r to the n plus 1. And now we just have some basic algebra. We can factor out this s. We'll have 1 minus r is equal to a. We can factor that out. 1 minus r to the n plus 1. And you can write that down if you'd like, but I'm going to erase it. We have s is equal to maybe I should have left that up. I'll leave that up, actually. Leave that part up. We have, so far, that s is equal to a times 1 minus r to the n plus 1 all over 1 minus r. And this looks complicated, I agree, but it's actually a lot simpler than it looks, because we have to think about what values of r does this series converge for. And we could do a more formal proof of this. I kind of want to do a more formal proof of this, but I think it's better for us to just sort of think about this with our brains, right? We're mathematicians. We can do this. We can think, how does this work for specific values of r, right? And if r is, I'll give you like an edge case and you can consider it in your head. But if r is equal to 1, we have a plus a plus a plus a plus a plus a plus a, right? So r can't equal 1 because if a is a value, you will just be increasing to, infinity, and you will get a diverging series, right? So r cannot equal 1. Can r equal 0? Not, well, it can, but it's not technically a series at that point, right? Because, well, I suppose it is a series, but you're not. Every n isn't changing anything. You're just adding um, values, right? And technically, technically, the series does converge if r is equal to 0. So you can think of it as 0 is less than r is less than 1, but r can be negative, right? Like we were talking about alternating series, and even for diverging series, if there is an alternating part, series like the harmonic series or series that actually do decrease will converge if there's an alternating part. So it can be negative, but it can also it equals 0, and it cannot equal 1. Hope you're starting to think of it a little bit, but if you have guessed, we are using some kind of absolute value, right? Because we have negative values that are possible. And again, it cannot be like negative 5 over 3. Like, it can't be less than negative 1, because you will be subtracting higher and higher values, and you will be diverging to negative infinity. So we'll say that the absolute value of r is less than what? We said r cannot equal 1, and I sort of spoiled it, but r can't be greater than 1 either, right? Let's think about r is equal to 2. So if you have a plus 2a plus 4a plus 8a, you're gonna get to a value that is constantly increasing for every subsequent n, right? So the absolute value of r has to be less than 1. It is a fraction, and it is a fraction that is less than 1. That is the idea behind these series. And if we acknowledge that these series can only converge if the common ratio is a fraction whose absolute value is less than 1, then we can simplify this sum to be specific to series that we know converge. For this type of series, or we can say this is actually a partial sum up to n plus 1. We can say that this works for partial sums up to n plus 1. But for infinite series, if we say that r, the absolute value of r, is less than 1, and you plugged in a very high n value, let's say, because, again, n is approaching infinity, right? You have essentially an infinite n value, and if you plugged in an infinite n value, you're going to have r, which is a fraction whose absolute value is less than 1, so it's going to be like 1/2, 1/3, 4/5, 9/10, whatever. That absolute value is less than 1, and if you raise it to a really high value, you are getting closer and closer to 0, right? The same reason why 1 over infinity approaches 0 is the same reason why 9 over infinity approaches 0, and why 9 over 10 to the infinity approaches 0, because these are fractions, right? And the fraction itself is going to decrease as n increases. So as this r is a fraction whose absolute value is less than 1, r to the n plus 1 will go to 0, right? You'll be having a fraction that is less than 1 to a very high value, right? N plus 1. And so you're going to get 0, which means that the sum for our geometric series, our infinite series, is just going to be a over 1 minus r. So yeah, and if the fraction is 1 over some value, like not gonna find a good example, but if a is like 1 over like 2 or 3 or something, then you can also generalize this to just be 1 over 1 minus r. But yeah, pretty okay, I should say. And I know we didn't go into a more formal proof of why geometric series converges, but if we acknowledge that r is a fraction whose absolute value is less than 1, that does fit the nth term test, right? If you plug in the limit as n approaches infinity of some r whose absolute value is less than 1 to the power of n, you will go to 0, right? So it does fit the nth term test, which means that it is a potentially valid series. And we were actually able to, calculate what the value of the series is. A over 1 minus r. Let's write that one more time. A over 1 minus r. And now we have a couple more series to get through, or a couple more tests to get through. Okay, so I've been a little bit coy about this new test that we're going to be doing, the alternating series test, and that's because I have only now recently seen a proof of it, and though I think it makes sense, it is also something I'm not very familiar with, and I don't feel super comfortable teaching, but, I am still just a kid, and we're going to figure it out from here. But let's talk about what the actual alternating series looks like. It's not a superscript n, it is a sub n. So an alternating series is a series with an alternating part, right? It is a sequence with an alternating thing that is attached to it. And by alternating, I mean that it goes from negative to positive. So negative 1 to the power of n is alternating, cosine n pi is alternating because, you go cosine pi to cosine 2 pi plus cosine 3 pi plus cosine 4 pi. So you're going from 1 to negative 1 to 1 to negative 1. The same thing with negative 1 to the n, obviously. And so when you plug in n equals 0, you're going to have an even power of n, so you're going to have a positive number, which means that you're going to have a 0 minus a 1, because, if you plug in 1, you're going to get a negative. And you're going to get an odd value, which will get you a negative. So minus a1 plus a2 minus a3, and, on and on. And this is called an alternating series. And the alternating series test is rather special. It makes almost every alternating series that you see very easy, at least in my opinion, to prove whether it's converging or not converging. And that is, it only has two things to say that a series is convergent, conditionally convergent, because again, this is negative 1 to the n, which means that if you take the absolute value, you will ignore the alternating part, and therefore it may or may not converge. Most likely will not converge. So if you have an alternating series, it's a relatively safe bet to say that it's conditionally convergent, but you can have a alternating geometric series or an alternating p series that is convergent regardless of whether or not you have an alternating part, and those are absolutely convergent, because if you took the absolute value of every single term and added them up, you'd still get a convergent series. So the alternating series test works and says that if you have a series of this form, an alternating series, and a sub n decreases monotonically. Again, we described what monotonic decreasing looks like in the sequence video, but just generally, as you get through higher and higher values of n, a sub n is approaching smaller and smaller values, and every subsequent term, so a sub n plus 1 is going to be less than or equal to a sub n. And, of course, the limit as n approaches infinity of the sequence should also equal 0, because, again, we need to do that nth test for divergence whenever we can. And to prove this, again, I'm not super familiar with this, but I think it makes sense if you just sort of think about it. So if you have this alternating series from n equals 1 to infinity of negative 1 to n times a sub n, and those kinds of sequences, you should also be able to prove that both the partial sums of like series with odd numbers of terms and series with even numbers of terms, if regardless of whether there's an odd number of terms or an even number of terms, it converges to the same value, then it doesn't really matter if you have a negative or a positive at that specific value, as long as you are still converging to the same value. So this proof is essentially saying that if you have a partial sum up to, say, 2m plus 1, which is going to be an odd value, right? You have an even number and then you're adding 1 to it, and you're doing the series from n equals 1 to, or the partial sum from n equals 1 to 2m plus 1 of negative 1 to the n minus 1, so that we have an, so we have a positive first term times a sub n. If this, if this is convergent and this is convergent, so if you use an even number, 2m, n equals 1, negative 1 to the n minus 1, a sub n. If both of these converge, and both of them converge to the same value, it doesn't matter whether the number is negative or positive, but the larger series is converging. So if this is true, then sk, as we've said, the sequence of partial sums should equal, from n equals 1 to k, and negative 1 to the n minus 1, a sub n. So if this converges to the same value as this, that means that this also converges to L. So that's how this is proved, right? And so these odd partial sums, so let's start with the odd partial sums. I'm just taking this straight from the article that I'm looking at. If this sequence decreases monotonically, so if n plus 1 is less than n, the n plus 1th term is less than the nth term, then s sub 2 times m plus 1, or s 2m plus 3, yeah, s2m plus 2 plus 1, okay, good, I can do math, s2m plus 3, right? And that should be equal to the sum up to 2m plus 1, right, minus a 2m plus 2 plus a 2m plus 3, right? Because you should be able to sum up every single value up to 2m plus 1 and then use the alternating values. So if it's an even value, if you add a 1 just fully, you should just get a positive, negative coefficient. And if you have 2m plus 3, which is an odd number, you're going to have an even coefficient, or positive coefficient. So you have this partial sum up to 2m plus 1, and then you have the terms that are left after this partial sum up to 2m plus 1, because you are doing the partial sum up to 2m plus 3, right? And then this is less than or equal to the sum up to 2m plus 1, right? Because this is what the definition was saying, that this is monotonically decreasing, so a sub n plus 1 should be less than or equal to a sub n, the absolute value. So we have this idea fully written down, and the even partial sums will be increasing monotonically. So you have s 2 times m plus 1, so you have s2m plus 2, which is the sum up to 2m, plus a 2m plus 1 minus a 2m plus 2 less than or equal to s sub 2m, right? Because, again, the terms that come after should be less than the term that came before. Yeah. Okay. Okay. Yeah, that makes sense. I'm trying to think of this myself. Okay. Yeah, no, I get it. Because what they're saying is that you should be able to subtract, 2m from 2m plus 1 and get one term. So you can write that down if you'd like, but I'm just going to erase this. You have to be able to subtract the even terms from the odd terms, because 2m plus 1 is obviously 1 more than 2m. So you're going to be left with s of 2m plus 1 minus s sub 2m is equal to a 2m plus 1, right? It's the sum up to 2m taken from the sum up to 2m plus 1, so the only term that's left out is a sub 2m plus 1, and this is going to be greater than or equal to 0, right? So now we have a good amount of information here, right? We have a1 minus a2. So yeah, the first two terms, like we said that you start off with a0 minus a1 plus a2, but since we're starting at n equals 1 instead of n equals 0, we're going to have positive a1 minus a2, and that's going to be equal to the sum up to the first two values. Remember, because we're just adding up the first two values, right? Since it's alternating, we're going to have this is less than or equal to the sum up to 2m, m being some undefined number, and this is less than or equal to the sum up to 2m plus 1, which makes sense, right? This is the sum up to 2m plus another term, which is less than or equal to the sum up to 1. So the last possible value, which is a1, like the first value. So if this sequence is monotonically decreasing, or a1 minus a2 is monotonically decreasing, a1 minus a2 is the lower bound of this monotonically decreasing sequence, s sub 2m plus 1. As we've said, this is the monotonically decreasing sequence, while s sub 2m is the monotonically increasing one. That's the even partial sums, which means that this sequence converges because this is monotonically decreasing. This sequence converges as m approaches infinity, right? So the limit as n approaches infinity of s sub 2m plus 1 minus s sub 2m should be, again, the limit as n approaches infinity of the value that's left over if you sum up to 2m, and you sum up to the term that comes immediately after. The one value that you're left with is the term that comes after the partial sum up to 2m. So you have a sub 2m plus 1, and that's going to be equal to 0, right? Because we said this was less than the one that came before it. This is monotonically decreasing. So if you have, m approaching infinity, we said that this is approaching 0, right? Or, well, you said this sequence converges, but, this has to equal 0. And, yeah, so that means that if you plug this back into our inequality, we have the limit is in between the sum up to 2m and the sum up to 2m plus 1. So that's why the even ones were monotonically increasing, so that we'd have a limit that's above that, and this is why it's monotonically decreasing, so we have a limit that's below So we have something that's in between those two values, and this works for any m, so any even or odd value, which means that regardless of what position you are in within the alternating series alternates above and below the limit. So it should converge to the same value regardless of whether you're having a plus or a negative at that specific term. I understand that this is a very confusing proof. Honestly, I'm a little bit tripped up. Like, I would say I get maybe 70% of this proof. Like, the idea behind it makes sense. You just want to say that if you have a partial sum with an odd number of terms and a partial sum with an even number of terms, if they both converge to the same number, then the alternating series as a whole should converge to that same value, therefore proving that this series works if it decreases monotonically. The reason why I'm a little bit tripped up is where the even partial sums increase monotonically, but I suppose that does make sense because you're trying to bound the limit between the sum up to 2m and the sum up to 2m plus 1. So I think it's more like you're asserting that the even partial sums increase monotonically and the odd partial sums decrease monotonically, so that you can set up this inequality at the end where you have the limit is greater than the sum of even partial sums and less than the sum of odd partial sums. And then I would say this part makes mostly sense. Yeah, no, because so this part makes sense, obviously, and then this is what's left over from there, and since n plus 1, well, the n plus 1th term is less than the nth term, because that's what we're asserting. If this is a, like, monotonically decreasing function, that means that s sub 2 should be less than s sub 1, which we said was equal to a sub 1, right? It's the first term if it's the sum of, well, every term up to the first term, which is only the first term. So yeah, I would say that this, now that I've like explained it to myself, I suppose it makes more sense. But yeah, that's a very confusing proof, and I mean, it's pretty cool. I guess it is pretty cool, but yeah. So that was the alternating series test. That was quite the long proof for quite the simple concept. If you have an alternating section of your sequence and your sequence is monotonically decreasing, which means that the n plus 1th term is less than the nth term, or less than or equal to the nth term, that means that every single subsequent term is less than or equal to the terms that came before it, and it's alternating, which means that it has to converge, and it will converge conditionally because of that somewhat strange proof. And another really important idea behind alternating series is our errors. So the alternating series error bound, just like, we're gonna go over this pretty quickly. I'm planning on doing another video where I go over some of the more intricate tests. I'd say like the ratio test, the direct comparison test, limit comparison test, root test, some of like the scientist named tests, because there's a bunch of, not scientists, mathematicians. So yeah, let's just let's do this one. So we have the sum up to k values. We're gonna again write this as n equals 0 up to k of negative 1 to the n with a sub n, and if this is the sum up to k minus the L. So if we just think about this, if the sum up to k is the partial sum up to, k number of terms, and L is the actual limit of the series, this should be less than or equal to the sum up to k minus the sum up to k plus 1. Again, this will be a positive value because every term is less than the term that came before it, but just so that we're perfectly clear on what's happening, you are essentially taking up, Like you're taking the sum up to a certain number of terms and you're subtracting it by what the value is actually supposed to be. And then you are saying that the sum up to k minus the sum up to k plus 1 is greater than or equal to this very small difference in between the partial sum and the actual limit. And the sum up to k is 1 less than the sum up to k plus 1. So this sum up to k minus the sum up to k plus 1 is just one value, the k plus 1th term. So that's really cool. It's essentially saying that the error between the sum up to k and the actual true limit of this series is just the term, the k plus 1th term. So if you're summing up to k and you're trying to see the difference between the limit, like the distance between the limit and the actual and the partial sum that you've calculated, you just set an inequality less than or equal to the term that comes immediately after it. Like, that's really cool. And it kind of blew my mind when I saw it. So this proof is also relatively short. It is another odd even proof, so I'm not super familiar with it, but it's just like if you think about that, like it makes sense, you know? Like I think at least the sum sub k s sub k minus s sub k plus 1 is equal to a sub k plus 1. That makes sense. But the s sub k minus l, that's a little bit of an abstract concept, but it's just the distance between the sum value that you've calculated and the actual limit value. But let's say that when k is an odd value, you have, let's just plug it straight in. If you have s sub k minus l and k is an odd value, you have s sub 2m plus 1 minus l is less than or equal to s sub 2m plus 1 minus s 2m plus 2, right? You have, well, this is less than or equal to s sub k minus s sub k plus 1. Yep. And, well, you need to do absolute values, but, you know, for this part, I'm just going to sort of illustrate this idea. And this is, again, equal to the term that is left over after this calculation, and that is, well, a sub 2m plus 1 plus 1, or a sub 2m plus 2, right? And then when k is even, so when you have s sub 2m minus l, s sub 2m minus l, and that's less than or equal to, well, wait. Okay. So, again, this is monotonically increasing, right? So we're just going to rewrite this as a switched sort of thing. You know, if we make these negatives or inverses of their original value, then we can flip the sign so that it's monotonically decreasing. We go back to our less than or equal to, because that's a little bit, you know, nicer to look at. We have L minus S sub 2m, and that's less than or equal to S sub 2m plus 1 minus S sub 2m, and again, the value that is left over from this is just the term that's left over. You have the sum up to 2m and the sum up to 2m plus 1, so the one term that's not accounted for is a sub 2m plus 1. So, yeah, in this previous proof that we did, you know, we have the same type of inequality. We have S2 less than or equal to S2m less than or equal to S2m plus 1. It's less than or equal to S1, right? And this is A1 minus A2, and this is A1, and you're just saying that if the limit, like if the term falls within this inequality, then, you know, the concept is proven. And yeah, I I'm actually not sure if I like that proof. I feel like it's a little bit strange. I There's apparently another proof that we will most likely go over in good time. But I think for today, that's probably it. Again, there's obviously going to be another series video. We are just getting started. We have so much more practice, so much more stuff to do, and I still haven't done the addendum to the sequences video, so I have a lot to record and a lot to talk about, especially in terms of partial sums for sequences, because that is a very interesting topic, especially for geometric series and arithmetic. Wait, what? Geometric sequences and arithmetic sequences. There are some really cool sums and like proofs for those sums that I've always thought were interesting. Like the sum for one of the arithmetic sequences was one of the first like proofs that I've ever seen, and it like blew my mind when I saw it. But yeah, I think for now it is rather late. For now, I'm gonna stop the video off on here. I know this is not the best note to end on, especially because we didn't go over nearly as much as I wanted to, but still in the mood for a song recommendation. And let's see, let's see what I've been listening to. Uh, this is gonna make me sound like a huge weeb. I mean, city pop isn't like that bad. I would say city pop is pretty widely accessible, but there's this album called 82 Love Trip by this one singer named Takako Takako Mamiya. I'm really hoping I'm saying that right because she deserves better than my mispronunciation. This album is fantastic. Less instrumentation. Her voice is like really well developed, especially considering this is her only album and this is evidently a pseudonym. She just sounds like she's been doing this professionally for years, and it just sounds fantastic. Like the soundscapes are just really well produced. It's just jazzy and soulful, and it's just good listening. It's like it's like driving at 3 a.m. in like rain, but not in like a dangerous way, but more like in a, you know, it's dark out and mysterious. Okay, it's dark out and mysterious, and the road's completely empty, and you're just alone with your thoughts, and you're sort of just listening to this stellar album. Like I don't even know a single word that's happening. The first song is called Chinese Restaurant. I have no idea why, but it is just fantastic. Like I can't even truly describe how much I really like this album. Like even though it's not, I wouldn't say it's, I might even say it's one of my favorite albums. It's just like it's only been in my like life for a couple of weeks now, but I've listened to it a good, I'd say 7 or 8 times over the past couple of weeks, and I would say it's worth it. It's just good. Like it's hard to even explain. And I've heard a couple other city pop like records, not full albums, but just like singles, and this is just, I wouldn't even say it's like defining of the genre, but it's more like emblematic of the genre. Like I feel like this is a pioneer. Like I'm gonna spoil one of my album recommendations in the near future, but Chega de Saudade by Jose, like the samba, not samba, the bossa nova record. It is special. Like even if it's not like generic by any means, it is definitive of the genre. And I would say that 82 Love Trip is slightly off center from the normal city pop type of like sound and voice and like aesthetic, but it does what it's trying to do very well. I would go so far as to say perfectly because I don't know how good the songwriting is, or like I don't really even feel any need to criticize the production. I'm not like a music expert or anything. I would just say really great album, really well made, really entertaining. Um, and it's just a really nice listen. Like I can't even explain it any further than that. But yeah, fantastic album. And yeah, if you like this video, please comment down below. If you did not like this video, totally understand. Constructive criticism is always encouraged. And if you're not in the mood for a comment or constructive criticism, I've been doing I've been doing these really weird, like these bend over single hand dumbbell rows, I think it's what it's called. I might need to search that up, but you just like bend over and then you do a row with a dumbbell, but you only use one hand and you keep your like full body as straight and like, you know, I really hate to say engaged as possible, but you just sort of like activate your body and try to keep it as stable as possible while you're like pushing and pulling this one weight without like offsetting your core. I sound like a crazy person, but yeah, I mean it's a very fun exercise. I am still sore and I worked out 2 days ago, so pretty intense. So yeah, do some bend over single arm dumbbell rows. All right, so bye. It's very late. If it's not obvious, I sound inebriated, I'm sure. Bye.